Information of modern materials come from three sections: Chapter 11, Section 7, Chapter 12, Section 7, and Chapter 12, Section 8. We split modern materials into two segments. In first segment, we discuss about liquid crystals. So let me write down liquid crystals, polymers, and biomaterials. There are some substances like cholesterol, benzoate. When heated, they pass from solid state to an intermediate state, which is liquid crystalline phase instead of just a pure liquid. So liquid crystals have some of the structures of solids and some of the freedom of motion of liquids. So you can say that this property in between is solid and a liquid. Now, uses of liquid crystals: pressure and temperature sensors, display of electrical devices like calculators, laptop computers, watches. So liquid crystals are used in those display units. Now, basically it works like this. When there is an applied electric field, there will be a change in orientation of the liquid crystal molecules, and those changes change optical properties. Now, we're going to discuss following types of liquid crystals. Nematic liquid crystalline phase. As you can see here, normal liquid would have randomly organized molecules. On the other hand, nematic liquid crystalline phase has molecules aligned along their long axis. If you look at these, they're aligned along the long axis. Second type is called smectic. There is an additional ordering beyond nematic phase. You can see that ends are aligned. So based on alignment types, smectic phase can be of following types: A, B, or C. Here we are going to discuss about cholesteric liquid crystalline phase. You can see that molecules are aligned along their long axis as in nematic liquid crystals. In addition, they are arranged in layers with molecules in each plane twisted slightly relative to molecules above and below. Now we are going to talk about polymers. They are made up of monomers or small units. For example, a starch molecule is made up of large number of glucose molecules bonded back to back. Polymers are usually amorphous or non-crystalline. Since they're non-crystalline, they do not have a sharp melting point. Rather, they melt over a range of temperatures. When blended with substances often called plasticizers, these polymers often become more flexible. So their property could be changed by adding some other substances. Now there are substances which bond between polymer chains, and they are often called cross-linking and provide rigidity to a polymer structure. Natural rubber is a polymer of isoprene, becomes harder when sulfur is added to cross-link. So sulfur basically acts like a bridge holding more than one polymer structure together. Here we're showing you formation of a polymer, especially the addition polymer. In polymer formation, especially in the lab, need to have something that would initiate the chain reaction like this. So you can see that how the double bond is broken and one is bonded to one side and the other one is bonded to the other side of carbon. And so eventually a long polymer is formed. Now, usage of addition polymer. In films, packaging, bottles, you use polyethylene. Polypropylene is used in kitchenware, fibers, and appliances. Polystyrene is used in packaging, disposable food containers, and insulation. Now, polyvinyl chloride is used in pipe fittings, clear film for meat packaging, and these are some uses of addition polymer. Condensation polymer, in which water goes out as polymer formation happens, like amine and carboxylic acid give amide and water. So polymer types could be the following: polyurethane or polyamide link. In this kind of link formation, water gets out, and that's why it's also called condensation, polymerization. Auto parts, footwear. Now, magnetic tape, soft drink bottles, home furnishings, and in all these cases, polymers, especially the condensation polymers, are used. The names of these condensation polymers are on the right hand side, like nylon 6,6. Here we're going to discuss different types of polymers and their properties. Like plastic is a type of polymer that can be formed into various shapes by heat and pressure. Thermoplastic can be reshaped after melting. Thermosetting plastic cannot be reshaped readily. So as you can see, their properties are not all the same. Elastomer, they would show elastic property. Non-elastic fibers like nylon or polyester can form fibers, and that could be used in fabrics, clothing, tire. Next important topic is biomaterials, and these materials have medical applications as in implant device, and they find use in diagnostic purposes, monitoring glucose level in the blood, contact lens, dental cavity filling, and all these purposes these biomaterials are used. Now, what characteristics implant device must have? Obviously, they should be biocompatible and should not cause any adverse immune response. Now, you need to be careful about this. The foreign objects in our body are usually bound by antibodies, and they're often rejected. Secondly, larger objects can induce inflammatory reaction, so you don't want that either. Also, some materials are more compatible with body tissues and fluids than others, so one will have to be careful before selecting an implant device. Now, physical requirements. This implant device must have strength, flexibility, and rigidity. So all these physical requirements should be there. Chemical requirements: it should be non-toxic, non-reactive, it should not be reacting with the body fluid, and it should not degrade, because in our body we may have different level of acidity and different chemicals out there too. Now, examples of different applications can be mentioned here. Heart replacement and repairs, one can use this, biomolecules. Vascular grafts, replacement for segments of diseased arteries. Artificial tissue, like lab-grown skin. Hip replacement, artificial joints. In all these cases, one can use biomaterials.